Welcome to part 3 of my lecture series on residuals in CFD. By now, if you've had a look at the CFD user manual for whatever code it is you're using and had a look at the section on residuals and scaling and normalization, you've probably noticed that the mass imbalance, or the continuity error as it's sometimes called, is treated differently to the other residuals in the CFD solution process. In today's talk, I'm going to be showing you why that is the case. I'm going to be looking at a simple example and going through and explaining why the mass imbalance is treated differently. And this is going to result in us going through the process of normalization. And I'm going to be showing you why this is different to scaling. Because if you look through the user manual, you'll often find these terms referred to, scaled residuals, normalized, raw residuals. And by the end of this talk, you can have a really good idea of what the differences are between those two different mathematical techniques and how we apply them for the continuity or the mass error. So this is going to be forming another piece of the puzzle in understanding how residuals are treated in CFD. This is going to be really good. Let's get into the talk. So let's start this talk off with an example problem. The example problem I've chosen to use in this talk is very similar to the example problem for the energy equation that we used in part 1 and part 2. And what we've got is, rather than 1D heat flow in a bar from a hot end to a cold end, what we've got is 1D flow in a channel with a single inlet and a single outlet. So flow will be coming in the left end of the channel and it will be going out the right end of the channel. And we're going to divide that 1D channel into 4 cells. So very similar to the energy equation that we looked at before. And what we're thinking is that to conserve mass, the thing we're really going to be interested in today, the mass flow rate coming in the left end of the channel must be equal to the mass flow rate going out of the right end of the channel within some kind of tolerance. And that same process also applies for the individual cells in the mesh, where the flow coming in the left face of the cell must equal the flow going out the right face of the cell within some tolerance for our solution to be converged. Now, in the same manner as the energy equation, the CFD code is going to use an iterative process to get a solution. And so while the CFD solution is converging, each of those cells, the mass flow rate coming in the left face of the cell will not necessarily equal the mass flowing out of the right face of the cell. And there'll be a difference here. And so for this particular example, if you think of the second cell from the left of that 1D channel, you've got 2.01 kilograms per second coming into the cell through the left face, and then 1.99 kilograms per second going out of the right face of the cell. They're very close, but there is an imbalance here in the mass flow rate. And if we just subtract the mass flow rate coming into the cell from the mass flow rate going out of the cell, we find that the imbalance is 0.02 kilograms per second. And this is the local mass imbalance for a particular cell in the mesh, and it's often called the continuity residual by some CFD codes, or the continuity error for that particular cell. And of course, for more complicated cells, if we're in 3D and maybe we've got tetrahedral cells or polyhedral cells, the process of calculating the mass imbalance for a particular cell is exactly the same. All that we do is we calculate the mass flowing out of each of the faces of the cell, and any mass flowing in, of course, will be a negative mass flux out. And if we integrate or add up all of those mass fluxes for all of the faces of the cell, that gives us the net mass imbalance for a particular cell. And you can see in that integral, we've got the dot product of the velocity vector at the center of the face with the unit normal vector, because of course that gives us the component of velocity normal to the face passing out of the cell, which transports mass with it. So if we calculate that integral, or the summation in discrete form, over all of the faces of a particular cell, that's going to give us the net mass imbalance for a particular cell in the mesh. And of course, what we do is we carry out this process for all of the cells in the domain, and each cell in the domain has its own mass imbalance. So for this particular mesh that we're considering with 4 cells, we've got 4 cells, and so there are 4 different mass imbalances. And we can arrange those into a vector in the same way that we did for the residual vector before. Each of the components of this mass imbalance vector gives the mass imbalance in a particular cell in the mesh, and they're all different. Now, as the simulation converges, of course, we expect this mass imbalance to reduce over time and tend towards zero. And if you were to plot this for this particular example case we're looking at with a mesh with 4 cells, for example, then you'd find that maybe in iteration 1, you'd have the mass flow rate through each of the faces of that mesh would look something like the figure on the left. And then, of course, as the simulation converges, those mass fluxes will tend towards a constant value, because for our particular case we're looking at, we've got a constant mass flow rate through the domain, and so all of those values will tend towards that flat horizontal line of constant mass flux through the domain. Now, you'll have noticed, of course, that because every cell in the mesh has its own mass imbalance, when we're tracking convergence, we generally don't want to track all of those imbalances. When we want to draw our line plot with a single value that converges, because it's a lot easier for us to track and to assess the convergence of our case. And the way that we do that is going from our vector of mass imbalances to a single value is the same way that we did for the residual vector in part 1 of this talk. And you can use the L1 norm, the L2 norm, or the L infinity norm to produce a representative mass imbalance for the mass imbalance of all of the cells in the mesh. And of course, the choice of normalization will vary between CFD codes. But the important thing is that we're getting a representative value for how does the mass imbalance look for all of the cells in my mesh. And then we can track that single value to judge convergence. Now, you'll remember when we looked at the energy equation in part 2 of this lecture series, we introduced the idea of scaling and why scaling was so important. And the reason for scaling, of course, is that if we have an energy imbalance of 10 watts in a particular cell, for example, that doesn't tell us actually how close we are to convergence, because the important thing is what is that energy imbalance relative to the energy flux passing through the cell. And we have the same idea for the mass imbalance, where if we had a mass imbalance of 0.02 kilograms per second, for example, that doesn't tell us how close we are to convergence. We need to express that mass imbalance relative to the mass flux through the cells. And in the same way as the energy equation, I've got 2 examples for you here on the slide where both of these meshes have the same mass imbalance of 0.02 kilograms per second in that second cell in the mesh, but relative to the mass flow rate passing through the 1D channel, which is 2 kilograms per second in the case on the left and 200 kilograms per second in the case on the right, we can see that actually the case on the right is much closer to convergence because the relative imbalance, or the mass imbalance relative to the mass flow rate passing through that cell, is much lower, is only 0.04%. And so the same idea of scaling applies here for the mass imbalance, and we would like to scale the mass imbalance if possible. And we could use the same formula that we used before for the energy equation to scale the mass imbalance. We could take our representative mass imbalance R and divide that by our scaling factor n, which this time would be representative of the mass flux through the domain rather than the energy flux through the domain. And if we have a simple geometry, or a geometry that we can look at and do some hand calculations manually, then we can often pick out what the mass flow rate would be ahead of time and use manual scaling for that. So for this particular case with the 1D channel, if we have a velocity of 2 meters per second, for example, coming in at a velocity inlet, then we can calculate the mass flow rate from that. And that will give us a representative mass flow rate for how the mass should be flowing through the domain for all of the cells in the mesh. And you could do the similar thing if you had multiple inlets or multiple outlets, for example. You can calculate ahead of time what the mass flow rate would be through each of those inlets and use that as manual scaling to scale your mass imbalance. You could do exactly the same thing as you would for the energy equation. Now, the difficulty with the mass imbalance and why the mass imbalance is different to the energy equation and temperature, for example, can be summarized with the case you can see here on the slide. Now, there are some cases in CFD where we don't actually know what the mass flow rate through the domain will be before we carry out the calculation. And this is particularly the case for flows in enclosures or cavities where we have our domain, but we don't have any inlets or outlets. So if you consider the classic example of a lid-driven cavity, for example, this is just a box where the top lid of the box is moving from left to right. This is of course going to move the flow in the cavity, and we are going to get a circulating flow in the cavity. But because there are no inlets and outlets, it's not clear ahead of time what the mass flow rate in the cavity would be. We don't have a flow passing through the cavity. And even if we knew what the velocity of that moving lid was, it's not clear at what rate that flow is going to be stirred in the cavity, or what even an appropriate representative mass flow rate would be. Now, this is also the case for natural convection-driven flows as well. If you have a CFD domain where you've got a pressure inlet and a pressure outlet, for example, with a heated surface, the heated surface will heat up the flow locally, reduce its density, and drive a natural convection-driven flow through the domain. And this will draw flow in from the pressure inlet and force flow up through the pressure outlet. But the flow rate, or how fast that flow has been driven through the domain, we don't actually know ahead of time until we've calculated the CFD solution. And because we want to track convergence, we want to be scaling that mass flow imbalance as the solution converges, we would need to know what the mass flow rate was going to be before carrying out the calculation. And so clearly this is something that we couldn't do for a natural convection driven flow. We don't know in general what, even though we've got an inlet and an outlet, we don't actually know what the flow rate is until we solve the solution. So for many CFD problems where the mass flow rate is part of the solution or we don't know it, we can't use that as a scaling factor. And this is different to the energy equation and the other equations where often we can. And that's the key difference in why the mass or continuity imbalance is treated differently. And this is particularly the case when we want to do automatic scaling. So with manual scaling, that's always going to be fine if the user can calculate an appropriate heat flux or mass flux to scale the residuals and the imbalances by. But generally for CFD codes, when the CFD code is written, we have to assume that we're going to have a really, really complicated problem where we won't be able to do manual scaling, and the CFD code needs to do some type of scaling automatically by itself. And so that's really what we want to be thinking about for the rest of this talk, is for the mass imbalance in particular, what would be a way that we could do automatic scaling? How could we get the CFD code to calculate some kind of representative mass flow rate through the domain? Now, of course, the first way to approach this would be to think, well, we managed to do this for the energy equation by extracting some values from the matrices. Could we do the same thing for the mass imbalance? Now, just as a quick reminder, you'll remember that when we looked at the energy equation, what we actually did was we took the diagonal coefficient of the matrix and we multiplied that by a representative temperature difference, and that allowed us to approximate what the heat flux through that 1D bar was going to be. And we used that for our automatic scaling factor n. Now, unfortunately, we can't actually do this for the mass imbalance, and the reason for that is that we don't actually formulate and solve the continuity equation as a matrix equation, particularly if we're using a pressure-based staggered solver that uses the simple algorithm, for example. We don't assemble and solve the continuity equation as a matrix equation in general. And so because we don't have a matrix equation, we can't take that diagonal coefficient and use that to get a representative mass flux. So what can we do? What does that mean? Well, I don't want to go into too much detail about solution algorithms and how the CFD code actually calculates the solution of the flow and of the flow fields. But briefly speaking, it's worthwhile thinking about what actually goes on, particularly in a segregated solver that uses the simple algorithm, for example, because it does help improve your understanding of what's actually going on and why. Now, if you use the simple algorithm to solve the flow field using a CFD code, what happens is that the CFD code first solves a matrix equation of the form AU equals B to calculate the x component of the velocity at the centroid of every cell in the mesh. So U1, U2, U3, and U4 will give you the U velocity at the centroid of every cell in the mesh. Then we do the same thing for the V momentum, or the vertical velocity component. We solve another matrix equation for V1, V2, V3, and V4. And then if we're in 3D, we solve a third matrix equation for W1, W2, W3, and W4, which is the final velocity component at the centroid of all of those cells in the mesh. So we solve momentum equations to get us U, V, and W. And then what we do is we use the solution of those momentum equations to calculate the mass imbalance in each particular cell. So remember that formula that we introduced earlier for how we'd calculate the mass flux across the faces of a particular cell in the mesh. We do that as a post-processing operation after solving for U, V, and W. So this is the key conceptual point here, that with continuity and mass, we're not actually solving a matrix equation directly for mass. We're doing this as a post-processing operation on the velocity field U, V, and W that were calculated by solving the momentum equations. So for us and our purposes, with scaling the residuals, we know that we don't have a matrix equation, so we can't use a diagonal coefficient like AP to get a representative mass flux through the domain. Now, just as a small side point here, for those of you who looked at some of the algorithms like the simple algorithm, we do then solve a matrix equation for the pressure correction, which is used to adjust the mass fluxes during the next iteration. But the important takeaway from this point is that we're not solving a matrix equation for mass imbalance or continuity. So we need to do something completely different, and that's why continuity and the mass imbalance is treated differently by CFD codes. And what do CFD codes actually do? So we can't rely on a manual scaling factor. We have to have some kind of automatic scaling. What can we do? Well, actually, it turns out what CFD codes do is they use a process of normalizing the mass imbalance rather than scaling the mass imbalance. This is a different technique that we're going to be using. And normalization is something I'm going to go through and explain over the next few slides. And you'll see how normalization is different to scaling. And this will really help your understanding as you look at the convergence of the mass imbalance in your CFD simulations. So let's go back and let's think of an example, because an example is definitely the best way to understand what's going on here. And what I've got for you on the slide here is just a graph showing the variation of the mass imbalance in a particular mesh as a solution converges. Now remember that the mass imbalance here, this is just the mass imbalance for each of the cells in the mesh, the difference between the mass flow rate in and the mass flow rate out of a particular cell in the mesh. And then we've taken a representative value using the L1, L2 or L infinity norm to get a single value that's representative of the mass imbalance for all of the cells in the mesh, and then plotted that on a graph. And what you can see, these values they're not scaled, they're not normalized in any particular way. And so you can see that the initial mass imbalance right at the start of the simulation is around 100 kilograms per second, or 1e to the 2. And what we can see is that the mass imbalance, as we solve that CFD solution, the mass imbalance reduces. So by the time we get towards the end of our CFD solution, we can see that the representative mass imbalance is now around 1e to the minus 1. So it's a lot lower than it was initially when we started the solution. This is a good sign. Our mass imbalance has reduced. But what can we do about this? Well, actually what we're interested in, even just thinking about that graph there, is that we're reducing from 100 kilograms per second to 0.1 kilograms per second. Actually, what we're interested in is how much has that mass imbalance reduced, because we can't, as we've discussed before, divide that mass imbalance by the mass flux through the domain, because we don't know what it is. We could have a lid-driven cavity flow, natural convection, for example, and so we don't have a value that we can scale by. Instead, what we're going to do is look at, well, how much has it reduced? It's gone down from 100 and it's now to 0.1. How much has it gone down by? Well, just looking at that graph for this particular example, we can see that going down from 100 to 0.1 is 3 orders of magnitude. We can get that from the graph just by looking at it. But for general cases, it can be quite difficult to do, looking at the graph manually and trying to work out by eye how much we've gone down by. A convenient thing that we can do is we can normalize that mass imbalance by the maximum value. And what that means is if we just divide that entire line by the 100 kilograms per second, what that shows us is we arrive at the plot on the right. And we can see that when we've normalized the mass imbalance, we start at a mass imbalance of 1, and then we go down to 1e to the minus 3. So because we've got a logarithmic plot, we can quite easily see that our mass imbalance has reduced by 3 orders of magnitude. And that's what we can use to help us assess convergence. And this is very different. This process of normalizing or dividing by the maximum value is very different to scaling. And I really wanted to emphasize this point on this slide by giving you the equations. So when you actually look at the CFD manuals and the options in your CFD code, you can actually understand the difference between them, because it can be confusing. And with scaling, of course, we take that representative mass imbalance R and we divide it by a scaling factor n, which is representative of the mass flow rate through the domain. But with normalization, what we're doing is we're dividing by the maximum value rather than n. Otherwise, these two approaches are very similar. And it's very easy to get confused between these two approaches, but they are actually very different and they give you very different values. And I've put another example up on this slide just to really illustrate how different the values can be and why normalization and scaling are different things. And if you look at the case on the left, we've got the same case we looked at before. Our second cell in the mesh has 2.01 kilograms per second coming in the left face of the cell and 1.99 kilograms per second going out the right face of the cell. And this gives an imbalance of 0.02 kilograms per second, exactly where we were at the start. Now, the scaling factor for this problem, which we could have in this case because we have an inlet and an outlet and we know what the mass flow rate is, we could take 2 kilograms per second as our scaling factor, and that would allow us to calculate a scaled residual if we did it that way. But because we're early in the solution process, the maximum imbalance in this case would be 0.02 kilograms per second. And so if you were to divide those, you could see that your normalized imbalance would be around 1 because we've divided by that maximum value, but the scaled imbalance would actually be a lot lower. And you can really see this is the case in the plot on the right, where we're now looking much later in the simulation process, maybe at iteration 400, say, where the imbalance is now 0.02 kilograms per second. It's gotten a lot smaller. And relative to the mass flux through the domain, the scaled residual is about 0.1%, but relative to that initial imbalance of 0.02, you can see that the normalized value is actually around 10%, which is a lot larger. So scaling and normalization really do lead to quite different values. And even a simple example like this, it's well worth going through yourself, maybe with a pen and paper, and just setting up a simple example for yourself and trying to understand what the difference is between a scaled value and a normalized value, because they're really very different. Now, the next thing I wanted to talk about was if you now go ahead and look in your CFD manual, you'll often find that when a residual or the mass imbalance is normalized, it's often normalized by the maximum value in the first 5 iterations. And that seems to be pretty common in many CFD codes, but it's not often explained why you take the maximum value in the first 5 iterations. Why not the first 10? And why does it need to be in the first 5 iterations at all? Couldn't you just take the maximum value over all time? And if you think about this, if you had a CFD case where the solution actually diverges rather than converges and the mass imbalance increases over time, what would happen is that our normalized mass imbalance, we would keep picking a new maximum value and we would be normalizing by a larger and larger value. And that would lead to some erroneous behavior, where if we're dividing by a larger and larger value, we may think that we're not actually diverging. It may disguise the values. And so this is why we just often limit our normalization value to the value within the first few iterations, for example. It's to avoid this case where if we do start diverging, then the maximum value keeps increasing over time. And sometimes you need more than 5 iterations, or sometimes this does need to change. And this is often why that maximum of 5 iterations is often left as a variable for the user. And so you can look at your case and see what actually happens. And in most cases, the first 5 iterations is fine and it's usually okay. But if you needed to change it, then you could, for example. Now, what I wanted to do is to finish off this talk is we've discussed the difference between normalization and scaling, and we've now got a good idea of what the differences are. But what I wanted to do is just quickly mention a few limitations, because we've adopted the process of normalization for the mass imbalance really out of necessity. We would rather do scaling if we could, but because we need it to be general and some cases don't have any inlets or outlets, or we don't know the mass flow rate, we have to use normalization. And to understand some of the limitations of this approach, it's really worth going back and thinking about the natural convection driven problem again. And what happens in this case in particular is often the initial solution is often very slow moving, because it takes some time for the fluid to heat up and then reduce its buoyancy and then to start driving that natural convection driven flow. And because it takes some time or some iterations for the flow field to actually develop, the flow is initially very slow moving. And so the mass imbalances initially are actually very small. And this can lead to some erroneous behavior if we normalize by the mass imbalance that happens very early on in the solution process. And just to give you an idea of what happens to the graph in this case, if you take the case on the left where you can see just the unnormalized mass imbalance, you can see that for this particular case of natural convection driven flow, the initial mass imbalance is actually quite small. In this case, it's maybe 10 to the minus 2. So actually the mass imbalance is very small, but that's just because the flow is very slow moving. Actually, relative to the mass flow rate through the cells, that might actually be quite large. And so if we take that value for normalization, because it's the first value in the first 5 iterations, and then if we proceed through the CFD solution process, that natural convection driven flow will start to develop, the flow will be driven upwards and the temperature field will start to be developed, and we'll start to draw in more flow which feeds up into the plume in this case, for example. Then the flow rate will increase and the mass imbalances may not reduce by that much. And so what will happen is that if we normalize our mass imbalance by that initial value, then our final value relative to that may look like it actually hasn't reduced that much. And the problem with this is that as a user, this could lead to a CFD user such as ourselves looking at the results and saying that the mass imbalance or the continuity error is only down at 10 to the minus 2. So when we look at that, we may think my simulation is not converged, I can't use it, I need to look at something else. So whereas actually what's happened is it's just because we have normalized by a very small initial mass imbalance. And this is quite a common problem, and hopefully now you've got an idea about actually why this problem type tends to occur if you have a flow that's initially very slow moving. And this is why if you look in some manuals like the ANSYS Fluent manual, for example, they recommend also plotting and looking at the raw unnormalized mass imbalance, because that will actually give you a better idea of what's truly happening to the mass imbalance. And then you can use, once your natural convection driven flow has established, for example, or you've got your flow being drawn in from your pressure inlets and up through your pressure outlets, and you can look at the mass flow rate, you could then use that to do the manual scaling later. So you've actually got an idea of truly how large your mass imbalances are relative to the flow rate through your domain. And all of this hinges on the idea that the user is only looking at the residuals to assess convergence. So if you were only looking at the mass imbalance to assess the convergence of your natural convection case, then you might think that the case isn't very well converged, when maybe it actually is. And this is one of the reasons why we always need to remember in CFD that residuals only form a part of our overall assessment of convergence. As well as looking at residuals and the mass imbalance, we also need to look at other quantities like the global imbalance and some other quantities which I'm going to show you in the next talk. But that's really important to remember, that all of these residuals and normalization, it forms a part of a greater picture of how you assess the overall convergence. And I think that's very important to remember, that residuals are only a small part. So now let's just wrap up with a quick summary of what we've talked about in part 3 of this lecture series. And that is the main idea is that in the same manner that we looked at the residuals for the energy equation in the previous talk, we also have a mass imbalance in every cell in the mesh. And this is often called the continuity residual, and we can use it to assess convergence in a similar way that we did for residuals. And the way that we do that is we, of course, take a representative value of the mass imbalance of all of the individual cells in the mesh. And then what we would like to do is to either scale or normalize that mass imbalance, because the mass imbalance by itself doesn't actually tell us whether we're close to convergence or not. So a mass imbalance of 10 kilograms per second in a particular cell, for example, doesn't tell us if it's close to convergence or not. If the overall flow rate through the domain was 100 kilograms per second, then the error in that case is 10%, which is very large. So we need to do something to that mass imbalance to help us assess convergence. And what we looked at in this particular talk is that the mass imbalance needs to be treated in a different way to the energy equation and the other equations, because we don't have a matrix equation where we can pull out a representative mass flow rate. And for some cases, like flows in cavities or natural convection driven flows, it's also not clear what that representative mass flux would be ahead of time until we calculate the solution. And this is the reason why CFD codes often use normalization rather than scaling when looking at the mass imbalance in particular. And they often take the value over the first 5 iterations as the normalization factor. But often that option is left open to you as the user if you want to change that. And the final point to wrap up with this video is that you've started to see how some errors in your interpretation of the residuals can lead to difficulties when you're assessing convergence. And what that means is that actually we need to look at more quantities so we can form an overall picture of how our case is converging. And the residuals form one part of that overall picture. And I'm going to go into more detail in this in the next talk. So that wraps up part 3 of my lecture series on residuals in CFD. In the next talk, which is going to be the final talk in the series, I'm going to be bringing everything together by talking about global imbalances and showing you how these are different to residuals and the mass and continuity error. And I'm also going to be going through a variety of different techniques to show you how you can bring everything together and really make a good assessment of the convergence of your CFD cases. So you're going to come away with fresh understanding and be able to assess the convergence of your own CFD cases. It's going to be a really, really helpful talk. I look forward to seeing you in the next video.